Hello, welcome to the solutions video for Unit 4, Lesson 3, Rational Thinking. So here we are with the Ready, Set, Go problems. It says, perform the indicated operation, show your work. So for our first one, we already have common denominator here of 17. So we can go ahead and add the numerators together and keep the denominator the same. So 5 plus 8, that gives us 13. And that is our final answer. Doesn't reduce, so we leave it as 13 over 7. Here, we have 3 over 10 plus 16 over 25. So since those denominators are different, the first step we need to do is find a common denominator. So a foolproof way of doing this, you can always multiply the two numbers together that are in the denominator, 10 times 25 to get 250. That's not the smallest one here, though. So we want to try to find a smaller one, ideally. So they can both be rewritten as with a denominator of 50, right? To get 3/10 to be something over 50, I multiply the top and bottom by 5 over 5. That's essentially like multiplying by 1. Same as multiplying by 1. This is important because that doesn't actually change the expression. It doesn't change the value that we get. So plus 16 over 25, well, to get 25 to become a 50, I need to multiply 25 by 2. So I need to multiply by 2 over 2 to, again, essentially multiply by 1. Well, that first part, 3 times 15, 3 times 5 is 15 over 50. 16 times 2 is 32 over 50. So now I have a common denominator. I can go and add their numerator. So 15 plus 32 gives me 47 over 50. That does not reduce. Always look to make sure and see if it reduces, but that one does not, so we are all set. So question 3, we have 4/5 plus 7 over 11. So again, we don't have the same denominator, so we need to think, okay, what can I multiply each one of these by so that the denominators are the same? In this case, the smallest one is what we get when we actually multiply the two numbers together, 5 and 11, which means I want to multiply 4/5 by 11 over 11 to create that 55, and 7 over 11 by 5 over 5 to create a 55 in the denominator. So 4 times 11, we get 44 over 55. Plus 7 times 5 is 35 over 55. Because remember, when we multiply two fractions, right, we created multiplication here. I do multiply the top times the top and the bottom times the bottom. So that's why we get 35 over 55. So let's add our numerators together. So 44 plus 35 gives us 79 over 55. And I honestly like to leave my answer like this because if I'm doing more with this, if I'm plugging this in, I think it's much easier to work with. However, if you notice, 79 is bigger than 55. So we could take 55 away from 79, which would give us 55 over 55 or 1. And we'd have 24 left over. So 79 over 55 is the same thing as writing 24 over 55. So either one of those answers is fine. Like I said, I prefer the 79 over 55, but it's a little bit easier to actually estimate what the value is when we pull that one out. Okay, so question 3, we're on to multiplication. And division. There's little divisions in here. I always like to try to look to divide first. It's going to make our numbers smaller rather than getting them bigger. So 2/3, there's no common factors there, and 4/5, there's no common factors. So I can't simplify either term there. However, always remember, we can always look top to bottom, no matter if they're in the same fraction or different, as long as there's no addition or subtraction. 2/5, those don't have a common factor, and neither do 4/3. So in this one, there's truly nothing that I can divide, no common factors to divide, so I go straight to multiplication. I do top times top, so numerator times numerator. 2 times 4 is 8, and 3 times 5 is 15. Always look to reduce There's nothing to reduce there. We would have seen it already if there was, so we're left with 8 over 15. So our next problem, we do have some things that reduce. So if I'm looking at just 2/3, nothing reduces there. But if I focus on the 2 and the 16, those both have a common factor of 2, so I can divide by it. I can divide by 2, which gives me a 1 here. Divide by 2, which gives me an 8 there. So I can reduce by a factor of 2. My 9 and 3 also have a common factor. These can both be divided by 3. So 9 divided by 3 is 3. 3 divided by 3 is 1. Okay, so let's see what we have left over now. In our first term here, we have 1 over 1, or first factor, I should say. And then we have times 3 over 8. So by multiplying by 1 over 1, it's really just multiplying by 1, which does not change our final answer. We're left with just 3/8. So you absolutely could have instead made this 18 over 48 to first. You could have done 2 times 9 and 3 times 16, but it's much harder to see where we can reduce if we do it that way first. Okay, so 10 over 33, nothing, no common factors there. 11 over 15, again, no common factors. But let's look at 10 and 15. Those are both divisible by 5. They both have a common factor of 5. So if I divide by 5, I get 3 here. And if I divide by 5, I get 2. So those reduce. And 11 and 33, I can divide both of those by a common factor of 11, which gives me a 1 here and a 3 here. So for our first fraction, we're left with 2/3. And for our second fraction, we're left with 1/3. So there's no more common factors to divide by, right? 2 and 3 don't have a common factor, neither do 1 and 3. So I'm going to go ahead and multiply the numerators. 2 times 1 is 2. And the denominators. 3 times 3 is 9. And that's in simplest form. So there we have it. So question 7 says describe your procedure for adding two fractions when the denominators are the same. So we've already talked about this a little bit. Like question 1 started that way. And we went ahead and we just added the two numerators together and kept the denominator the same. So we add the numerators and keep the denominators the same when they're already have the same denominator. Then always look to simplify. Look to, and I'll say reduce. Always look to reduce. Now question B, which is all the way down on the next page, when the denominators are different. So that was like question 2 and question 3. So notice the first thing we did there was find some factor to multiply each fraction by so that we actually do have a common denominator. So first we rewrite each fraction so that there's a common denominator. Then we go ahead and follow our same steps from part A. We add the numerators together and keep the denominators the same. And then lastly, reduce if possible. Reduce if possible. Okay. Let's move on to question 8. It says, explain your procedure for multiplying two fractions. So this one, there's a lot of different ways you could write. You could, what I like to do is look to see if you can reduce any common factors from the numerator and the denominator. Then multiply the numerators together. And the denominators together. That's not how you spell denominators. I want to note that these can be done in either order. So you can reverse order. You can multiply first and then reduce. I just always find it easier to reduce before we multiply, but you can do it in either order. Okay, let's go to question 9. So these are their set problems. So it says complete the missing features of each irrational function, sketch the asymptotes on the graph, and mark the location of the intercepts. So the first thing it says, what is the degree of the numerator? Well, we see that we have a 2 here. There's no other x's, so the degree of our numerator is 2. What is the degree of the denominator? The denominator is factored, so be careful. We have to add the multiplicities up. So 1 plus 1 is also a degree of 2. Since those are the same, remember the equation of the horizontal asymptote, we actually divide their leading coefficients. So the leading coefficient of the numerator is 1, and the leading coefficient of the denominator is also an imaginary 1 out front. So 1 over 1, we get a horizontal asymptote of y equals 1. So let's go ahead and sketch that on the graph. We're counting by ones here. So this is our horizontal asymptote, y equals 1, and I'll just label horizontal asymptote HA for short. Okay, it says equation of the vertical asymptotes. Well, this we want to look at the numerator. So these are going to come from the numerator. So here I have just an x squared. So if I set that equal to 0, I get x equals 0 plus or minus 0, really. So, vertical. I jumped down to, ignore everything I just said. I started doing the x-intercepts for some reason. Vertical asymptotes come from the denominator. So the denominator, right, this can't be 0. Can't equal 0. So I'm going to take each term from the denominator and set it equal to 0. So we have a vertical asymptote at x equals 6, negative 6, and if I take my x minus 4 and set it equal to 0, I get another vertical asymptote at x equals positive 4. So let's draw those in. So negative 6 is right here. So vertical asymptote x equals negative 6. And here is, well, there's 5, so here's 4. Positive 4. So those are my 2 vertical asymptotes for this problem. Now the y-intercept, well, we set x equal to 0. So we get 0 squared over 0 plus 6 times 0 minus 4. So it doesn't really matter what the bottom comes out to. We get a negative 24. But because our top is 0, that's going to automatically make our y-intercept 0. So we end up with the point 0, 0, which means that's also our x-intercept. Now, I kind of already started explaining the x-intercepts before, but this is where we're looking at our numerator. Right. The only way to get a y value of 0 here is to have the top of this fraction be 0. So when we're thinking of the x-intercepts, we want to think, okay, what would make this top 0? In this case, x equaling 0 would make the top 0, so we get an x-intercept of 0. So x and y-intercept are the same point in this problem. So there's question 9. Question 10. So, question 10 I'm going to rewrite down here. Y equals x minus 6 over x plus 3, since the equation and the space for it are on different pages. Alright, so let's go to question 10. So it says degree of the numerator. Well, I only see one x there. No multiplicity shown, so we're going to say the degree is 1. Same with the degree of the denominator. So, remember degree is the same. So we divide their leading coefficients. Well, their leading coefficients are both 1, so we get y equals 1 again. So let's draw that in. Horizontal asymptote, y equals 1. Okay, equations of the vertical asymptote, this is when we look at the denominator. So I take my x plus 3, and I say, okay, that can't be 0, really. I want to see what makes that term 0. In this case, a negative 3. So our vertical asymptote is at x equals negative 3. So 1, 2, 3, there we go. We do see that line approaching it, which is just a little bit of reassurance that we did do this correctly. So we only have one vertical asymptote in this problem. The y-intercept. So we're going to go ahead and set x equal to 0. So 0 plus 3, that gives us negative 6 over 3, or negative 2. So for our y-intercept, we have 0, negative 2. Let's plot that on the graph. We can see that it does cross right there at 0, negative 2. Okay, x-intercepts. Again, this is where we're looking at the numerator. We're saying, what would make x minus 6 equal to 0? Well, if I add 6 to both sides, I get x equals 6. So 6, 0 is my x-intercept, which I do see right here. 6, 0. Okay, that is problem 10. Let's go down to problem 11. So problem 11 gives us y equals 10x over x plus 3 squared. So the degree of the numerator is 1, and the degree of the denominator is 2. So this time, since the degree of the denominator is bigger, our horizontal asymptote automatically falls at y equals 0. So anytime the degree of the denominator is bigger, our horizontal asymptote is at y equals 0. Remember, we can cross horizontal asymptotes. So I see as I'm dotting this on that we're crossing the horizontal asymptote. That is okay. We are allowed to cross horizontal asymptotes. We cannot cross vertical asymptotes because that would make my problem undefined. So equation of the vertical asymptote, let's take our bottom, x plus 3, and I don't need to include the squared here because I can just square root and get rid of that right away. We will just want to think, what would make this term equal to 0? And that would having a negative 3 in there. So that's my vertical asymptote, x equals negative 3. So 1, 2, 3. So x equals negative 3 is the vertical asymptote. Remember, we can't cross those. Okay, the y-intercept. So again, I'm going to set my x value to be 0. So 10 times 0 over 0 plus 3 squared. Anytime we have that top turned to 0, it doesn't actually matter what the bottom is. This becomes 3 squared. I'll just write 9 right away. But it just becomes 0, which means this is also an x-intercept. We have 0, 0, which we see on our point there. So it actually falls directly on the horizontal asymptote. That is perfectly okay. So our x-intercept, we take our 10x equal to 0, which gives us x equals 0. So again, we have the point 0, 0 as our x-intercept. So there we have it. That's question 11. All right, let's go down to question 12. So question 12, again, the work is on a different page, so let's just move this question. Let's just copy it and move it down. I'm going to take a little screenshot and copy. There we go. Actually, let's get the number in there. Okay. So question 12. So degree of the numerator, right? Our numerator, our degree is 1. There's only one term there. But here we have 2 terms in factored form. So degree of the denominator is 2. Remember, whenever this is bigger, whenever the degree of the denominator is bigger than the numerator, our horizontal asymptote falls at y equals 0. So let's add that. We have a lot happening on this x-axis here. Y equals 0, horizontal asymptote. Okay, it says equation of the vertical asymptotes. Remember, this is where we look at the denominator. So I'm going to take my x plus 2 and set it equal to 0, which gives us x equals negative 2. And I'm going to take x minus 5 and set it equal to 0, which gives me x equals 5. So I have two vertical asymptotes at negative 2 and at positive 5. So x equals, let's do positive 5 first. Dot that on there. So vertical asymptote at x equals 5. And here's my negative 2. Now it does look like that line is touching it, but it's just getting infinitely closer. So sometimes it will look almost a vertical there, but the graph itself is not vertical. It's just getting infinitely closer to x equals negative 2 and x equals positive 5. And because we can only do so much with scale, sometimes that does make it look vertical. If I stretch this x-axis out, it would look much less vertical. Okay, my y-intercept. Remember, I'm going to set x equal to 0. So I'm going to say 0 plus 1 over 0 plus 2 times 0 minus 5. So that gives me 1 over 2 times negative 5, or 1 over negative 10. So our y-intercept is 0, negative 1/10, or negative 0.1 if you want. So it almost looks like it's falling at 0, 0 here, but actually that point is 0, negative 0.1. Actually, I'll write it as negative 1/10. There we go. There's our y-intercept. Okay, and our x-intercept, remember this is when we're going to take our top, our numerator, and set it equal to 0. So x plus 1 equals 0. That means x is equal to negative 1. So I have the point negative 1, 0, which is right here. Negative 1, 0. Okay, and there we have it. That is question 12. Notice none of those questions had what we call a hole in it, where we have a term in the top and bottom that's the same, but that's something we'll address later on. So our go questions. Rewrite each fraction in equivalent form. Then explain the mathematics that makes it possible to rewrite the fraction in its new form. So here, there's many possible answers. Many possible answers for each. So, because it just says rewrite it in a new form, in an equivalent form. It doesn't even say in a simplified or expanded. It doesn't give us much detail. So we'll typically try to simplify it when possible. So let's look at this one. Here we have a common factor of 3. So I can divide out that common factor of 3, which would give me 4/5. So that's an okay answer. You could also choose to, so here's another possibility. Answer is if we actually want to multiply both by, let's say, 2. If I want to multiply 12 by 2, I get 24. And since I multiply the top by 2, I'd have to do the bottom by 2 as well. So there's 2 different answers that are both possible. Like I said, there's many possible answers for both, for each of these. Okay, let's go to question 14. 26 over 11. I can't reduce this one. So let's write it, we'll read 26 is bigger than 11. So let's take 11 away, right? If I do that, 26 minus 11 becomes 15. So I could say it's 1 in 15 over 11. And hey, notice 15 is still bigger than 11. So I can take out another 11, which means I've taken out 11 twice, or I've taken out 22, which leaves me 4 over 11. So 4 over 11. So both of those are possibilities. Or I could make it bigger, right? I could say, okay, 26 times 2 is 52. and 11 times 2 is 22. So those are all equivalent forms. Again, there's many possible answers for each. I only show some. Okay. 51 divided by 17. Well, actually, 17, so 3 times 17 equals 51. So I can rewrite this as 3 times 17 over 17, which then becomes just 3. So I could just write this as 3. Again, or I could, now that I know it's 3, there's lots of different ways I could write it. I could write it as, let's say, 27 over 3, right? I could do lots of different possible answers once I know that it's 3. Okay, I'll just put that one answer for this one, but again, there's many possible answers. 6 over 13, we can't reduce that. They don't have a common factor, so let's make it bigger. Let's do 12 over 26. Or let's say we wanted to multiply it by 3 instead, right? 6 times 3 is 18. 13 times 3 is 39. So there's just 2 possible answers of many possible answers. All right, 114 and 27. So both of these can be divisible, so they have a common factor of 3. Remember, a quick way of telling that is if the numbers add to 3. 4 plus 1 plus 1 is 6. So 114 divided by 3. So I'm going to divide by 3 and divide by 3. So 114 divided by 3 is 38. And 27 divided by 3 is 9. So 38 over 9. I also might recognize that, hey, 9 is much smaller than 38, so I could write that as a mixed number instead, right? 9 times 2 is 18, so I could take out two sets of 9s, or I could think 9 times 4 is 36, right? 9 times 4 is 36. So I'm going to take away, so I'm going to bring 4 of them out, and that leaves me 2 left over. 4 and 2 ninths. So 38 divided by 9 is the same thing as 4 and 2 ninths. So those are 2 possible answers. Again, there's so many possibilities for these questions. All right, let's go down to question 18 and 19. I think those are our last 2 on this page. Yeah. So question 18. Notice I have a negative 14,529 and a positive. So common factor of 14,529, so I can just divide them both out and just make it -1. Here again, there's a few answers. I could notice that I can divide these. Now technically, we're assuming x does not equal 0 here, but if it was, then we'd have an undefined fraction anyways. Actually, I'll keep that. I don't need to erase that. Assume x doesn't equal to 0. We're also going to assume a does not equal 0, b does not equal 0, c does not equal 0, and d. Because if any of those terms were 0, we'd get something undefined. So we can assume that. So one possible answer, let's say we got rid of those. Or let's say, notice these are the exact same terms. So we could just say ax squared over ax squared. And that would be a possibility. Or the whole things cancel out. 1 over 1 is just 1. That's plenty of answers for that one. You only needed to find 1. So if you just put 1 for that, that's perfectly fine. And that's it for this Ready, Set, Go. So hopefully you found this helpful. Thank you for